Good afternoon, everyone. Good afternoon, everyone. Please, if you're online, indicate that you're online. We are about to start. If you're online, please indicate that you're online. Good afternoon, everyone. Please, if you're active, indicate your presence that you're active. If you're active, I hope you all can hear me. If you're active, please indicate that you are active. We are about to start. If you're active, please indicate that you are active. If you're active, please indicate that you are active. We are starting now. Please, if you're active, indicate your presence. Yeah, good afternoon, everyone. Please, if you're online, indicate your presence that you're online. If you're online, indicate. Please indicate. We're about to start. We're about to start. We're about to start. Please, guys, do me a favor. Let's keep on sharing. Let's share. Let's share. Let's share. Let's share the link. If you have shared the link, just indicate that you have shared the link. Please, if you have shared, let's share the link. If you have shared the link, please indicate that you have shared it. Share to your various departmental platforms. Share to your classmates. Share to every year one student. Share to every student that are in the science faculty. Please share. Please, let's keep on sharing. Let's keep on sharing. Please, if you have shared, indicate that you have shared. If you have shared, please indicate that you have shared it. Please, have you guys shared? If you have shared it, please indicate. Let's share the link. Let's share the link. People that are not replying, if you have shared the link, indicate. But please, while you are learning, share the link to other of your classmates while you are learning. Please, if you're active, indicate. The network is very bad, but we'll just try and manage. Okay, I want us to, we shall be looking at Chem 101 exam preparation class, all right, for mostly for those in Imo State University, because Alana, your exam is starting off, your chemistry is starting, will be taking other on Tuesday, right? Tuesday, and then the maths has been postponed already to the upper week, Tuesday and all that. So I'm looking at Chem 101. But before we start, please don't forget that we are meeting tonight. We're having an intensive class, Night of Revelation, from 8 p.m. to 4 a.m. This class will only last for 1 hour. Then after we are done with this class, we then meet rather by 8 p.m. from 8 to 4 a.m. For those of you who have been coming, you can testify that everything we taught, everything that we learned, everything that we reviewed in that Night of Revelation actually comes out 100%. Physics 101 was 100%. Biology 101 was 100%. Everything we learned, everything just appeared like a movie. All right? And I'm so sure that everybody that attended that class benefited and we're all happy at the end of the whole thing. So please ensure you join us tonight. All right, because this is online. I might be restricted a little so that I will not put myself in big trouble. So please take note. But let's look at Chem 101. The first aspect you should expect in your exam is under what we call chemical kinetics. Chemical kinetics. Then after this, we'll go into what we call Arrhenius equation. Then the third we'll look at under this, we'll look at how to balance a chemical equation. Balance of chemical equation. Then we'll go into chemical formula. Chemical formula. Then at the end, after this, we go into other aspects. Then we'll look at radioactivity. All right. We'll look at atomic chemistry. All right. We'll look at how to a little organic chemistry, because I'm suspecting this. Under this, we'll look at hybridization. We'll look at electronic configuration of elements. All right, and all that. Then we'll look at types of hybrid orbitals. A lot which can be discussed in ETC, but let's look at this first. Chemical kinetics, majority of us already know about this. When I say chemical kinematics or kinetics rather, in chemistry, we have what we call the reactant and the product, right? The reactant must have to combine to form the product. The study of how the reactant combine to form the product is called chemical kinetics. Chemical kinetics is an aspect of chemistry that studies chemical reactions, how the chemical reactants combine to form products is called chemical kinetics. The study is an aspect of chemistry that deals with the study of how reactants combine to form kinetics. Then the next one is, if we are saying that the study of how reactants combine to form, at which the reactant combine to form the product is called the rate of chemical reaction. So knowing chemical kinetics, you should also take note of what we call rate, right? Rate of chemical reaction. Rate of chemical reaction. Rate of chemical reaction is the speed or the rate at which the reactants combine to form what? to form product, there's always a rate, there's always a speed at which the reactant must combine water, right? Okay, if you look at this reaction, here we have 2 moles of water, here we have 4 moles of what? 2 moles of hydrogen. If you look at these 2 moles of hydrogen combined with what? 1 mole of what? Oxygen to produce what? Somebody 2 moles of what? Of water. I can also define rate of chemical reaction in terms of moles as it's also defined as the number of moles of reactant converted or product formed per unit time, because the reactant mole are always converted to form what? Products. So rate of chemical reaction is also defined as the number of moles of reactants converted or product formed per unit what? Time. Now that leads us to an expression used in calculating rate of chemical reaction. The rate of chemical reaction is defined as change in the concentration, absolute change in the concentration of reactants or products, absolute change over what? Change in what? Change in time. Absolute change in the conc of the reactant over change in what? In time. Okay, if we have reactant A plus B combining to form C and what? And D. What we are saying is that with respect to the reactants, the rate of reaction is change in concentration, absolute change in the concentration of reactants over what? Over change in what? In time. Over change in time. This implies that final concentration minus initial what? Concentration, absolute, over our change in time is final time minus what? Initial time. Please take notes. The word change simply means final concentration of the reactant minus what? Initial divided by final time minus initial time. Now, why do we have to say change? Because if reactant A and B react to form C and D, there will be a reduction in the concentration of the reactant because either A or B will be used up to form C and D. For there to be formation of product, that means the reactant must have to combine, must be used up, or must have to combine effectively, right? Okay, to form what? C and what? And D. Are you there? So the rate of chemical reaction is simply defined in respect to the reactant is defined as change in the concentration of the reactant over change in what? In time, which is same as what? Final concentration minus what? Initial concentration over final time minus what? Initial time. I'm going to solve a problem from your textbook, but I want us to just proceed. Let's proceed a little. All right, so let's move on. So that means in respect to product, rate is also defined as change in the concentration of product over what? Over change in what? In time. The same way we did for that of reactant will be used for that of what? Product. All right, so let's proceed on. Let's proceed. Now, I want us to know that. Take note of this as well. There are factors. Exam question. You might be asked to list the factors. List the factors affecting rate of chemical reaction. Rate of chemical reaction. You should know the factors by now. Number 1 is called temperature. Don't forget temperature. Number 2, we have concentration. also known as what? Pressure, also called pressure. Number three, we have surface area of contact. Surface area of what? Of contact. Number four, we have nature of reactant. Number five, we have light. Number six, we have catalyst. Number seven, we have time. Time is also a factor. All of these have their explanation. They might be asked to list them in the exam and explain one or two briefly. Temperature. Increase in temperature leads to increase in rate of chemical reaction and vice versa. All right? Okay. Concentration. Increase in concentration also leads to what? Increase in what? In rate of chemical reaction. Let me explain concentration because this will lead us to other questions you'll be expecting in the exam. All right? So all of these have their rates. Time. Rate of chemical reaction is inverse proportional to what? To time. Meaning that as time increases, rate with what? Will reduce. Increase in time leads to what? A reduction in what? In rates. So rate is always negative to time, but rate is positive to temperature concentration. So whenever you increase the temperature of the system, it will increase the rate of chemical reaction. Briefly, just that is all. Don't need to add any other thing, except we want to start talking about effective pollution and all that, effective reactants and the rest. But briefly is that increase in temperature leads to what? Increase in the rate of chemical reaction and vice versa. Then for concentration, when you increase the concentration of the reactants, it will increase the rate of chemical reaction. When I say concentration, it also means what? Pressure. Let's say, for instance, if reactant A plus B react to form C and D, right? So what we do is that as they are reacting to form C and D, a time will come whereby A and B will be used up. If A and B is being used up in the reaction, what we do is to add more. To proceed with this reaction, we have to add more of either A or B, of both, either. Now, addition of more of A and B simply means we are increasing the pressure or the concentration of what? Of the reactant. So when you increase the conc or pressure of the reactant, okay, particles or species, it will definitely increase the rate of chemical what? Reaction and vice versa. Under light, there are some reactions that can never occur without the presence of light. We all know that. A good example is called photosynthesis. Okay, we all know how catalyst speed up the rate of chemical reaction. Negative catalyst slows down, while positive catalyst speed up the rate of chemical reaction. Nature of the reactants. Some reactant particle has a nature, their chemical nature, that determines the rate at which they react. All right, chemical nature that determines the rate at which they react. For instance, the chemical nature of zinc is different from that of what? Of magnesium. That means that magnesium and zinc have different chemical nature that determines the rate at which they react. All right. Now the next is surface area of contact. The more the surface area, the more the rate of chemical reaction and vice versa. Surface area simply means, let's say for instance, you have ACl, ACl plus let's say a marble chip, solid marble chip, or let me use chalk, solid chalk, same as marble chip. That means the general language we all know. We all know what chalk, CaCO3, calcium carbonate, right? If I have a solid chalk and I put that solid chalk into ACl, then I have another chalk again. Let's say I have powdered one now. Then I put the powdered one into the same ACl. Which one do you think will react faster? is the powder, because the powder chalk have a large surface area. So the more the surface area of contact, the more the rate of chemical what? Reaction. So just take note of this. These are the factors. All right. But in case they said leads two major factors, the two major factors that affect the rate of chemical reactions are simply concentration and what? And time. The two major factors. But when they say list all the factors, list all of these factors. But for instance, when they say list two factors, please just list temperature and what? Concentration. They say list two. They say list three this way. They say list four. 1, 2, 3, 4. There's a list 5. 1, 2, temperature, concentration, surface area, nature of reactant, then light. Are you there? Please take note, just in this order. All right, so let's move on. You might be asked to explain or list, mention the things observed during a chemical reaction. The things observed during a chemical reaction. If we react ACl with powder chalk, what are the things you will observe? Things observed in a chemical reaction. One is what we call okay, odor, right? Number 2, we are going to observe solubility of the reactant, right? Of the reactant. Number 3, we're going to observe the color change, right? Color change. Number 4, we're going to observe bubbles or release of gas, right? Release of what? Of gas. All right. Number 5, solubility, okay, color change, bubbles, then it changes or its energy release. It changes, which can either be endothermic, right? Endothermic or exothermic what? Reaction. All right. So these are the things you're going to observe. When they say mention the things observed in the chemical reaction, just list all of these. All right. Okay. Now let's move down to concentration as a factor. This will take us to something very important. Concentration as a factor. I hope you guys are following. Please, if you are following, indicate that you are following. Indicate that you are following. Okay, concentration, we say that if I have reactant A plus B combining to give us what? To give us C plus what? D, right? We say that increase in the concentration of the reactant will lead to increase in the rate of chemical reaction, right? What does that mean? That rate of chemical reaction is that's proportional to what? To the concentration of what? Of A. Rate is what? Proportional to what? To the conc of A, meaning that if we should increase the conc of A, it will also increase what? The rate of chemical what? Reaction. Please don't forget. It will increase the rate of chemical reaction. So rate of chemical reaction is directly proportional to the concentration of A. Let's call this equation what? 1. The same rate of reaction is what? Proportional to the concentration of what? Of B. This is a direct relationship, meaning increase in the conc of B and in the conc of A will increase the rate of chemical reaction. This is equation 2. By the time we combine these two equations, that will give us rates. It's proportional to what? To the conc of A times what? To the conc of what? B. When you combine this, then when you take off this sign, that will give us the rate is equals to, I will introduce a constant called the rate constant, right? K, A to the power of X, then B to the power of what? Y. Where K represents the rate constants, S and Y represent what we call the order of reaction. Please note that K represents what? The rate constant. X, Y represent what? Order of reaction. Order of reaction simply tells us which of the reactants is reacting most. Is reacting more than what? Than the other. All right. Why we have to put X and Y? Because both A and B are not reacting at the same rate. They're not reacting at the same rate. So we have to use an unknown value, X and Y, to differentiate their rates. So where X and Y represent the order of reaction, okay, it tells us at what order is A reacting and at what order is B reacting. Is A reacting more than B, or B reacting more than what A? Or is A contributing most to the reaction, or B contributing most to the reaction? All right, okay. Now, this expression is what we call rate law. Rate law expression. We call this what? Rate law expression. We also call it differential rate law expression. Differential rate law. Differential rate law. Please take notes. If you are following, please indicate that you are following. If you are following, please indicate that you are following. The network is very bad. Okay, this is called the rate law, right? Expression. Now, you might be asked to state rate law. Let's state rate law. Rate law states that the rate of a chemical reaction, reacting species of a reacting species raised to a certain power. Raised to a certain power. The chemical reaction is proportional to the molar concentration of a reacting species raised to a certain power. Then the expression for rate law, if you are asked to state rate law and give the expression for rate law, after stating this, you have to start from here. That given the reaction A plus B to give us C plus D, the rate is proportional to what? Conc of A, rate proportional to conc of B. When you combine these two, that will give us the third equation. Then when you take off this sign, I will have to introduce a constant, an equal sign. And that gives us the rate equals to what? K, A raised by X, Y raised by what? B raised by what? Y. So this is how you're going to state in the exam. All right? Where K represents rate constant. The unit of K is not fixed, it varies depending on the value of your X and what and Y. So the rate constant unit is not fixed. Then X and Y represent the order of reaction. Then you might be asked to define the following terms. Define the following terms. The following terms. Number one, order of reaction. Order of reaction. Number two, first order reaction. First order reaction. Number three, second order reaction. Number four times first order, second order, and zero order. And also give the expression. Give the expression for each. Give the expression for what? For each. Okay? Give the expression for each. We said we have rate law expression. And I mentioned that this is called the differential rate law expression. There's what we call integrated rate law expression. Integrated what? Rate law expression. Differential rate law just show the relationship between concentration and what? And rates. Under differential, it shows an expression that connects how concentration is is affected by rate, or how rate rather is affected by what? By concentration. That's called the differential rate law. Then the other one is called the integrated rate law. The rate law shows us how changes in time affects concentration, or how time affects what? Concentration. That's under integrated rate law. But don't forget, you might be asked to differentiate between differential rate law and what? Integrated rate law. I'm going to list out all the integrated rate law expression for each of these order of reaction, and I will explain what order of reaction means. All right. Please, I hope I'm not too fast, because I want to believe that once I've come across it before, I'm just adding to our knowledge to expand us to be able to know that these aspects will likely show up in the exam tomorrow. Okay, so we have seen the differential rate law. Okay, this shows us, it's an expression that shows us how rate rate of chemical reaction is being influenced by what? Concentration of the reactant. All right. And we can see it here, that increase in the conc of the reactant A and B, we always lead to what? Increase in the rate of chemical reaction, because these two expressions are actually directly proportional to each other, right? Then when it comes to integrated rate law, it shows us how changes in time, or how time affects rate of chemical reaction. It is an expression that connects time with what? Concentration. But this expression connects what? Concentration with what? With rates. Don't forget. All right. So let's move on. Let's define order of reaction. Order of reaction. What is order of reaction? Order of reaction is defined as a power to which the molar concentration of the reacting species is raised to in the rate law. Order of reaction is defined as the power to which the molar concentration of a reacting species is raised to in the rate law. Is defined as the power to which the molar concentration of a reacting species is raised to in the rate law. That's called the order of reaction. Please, if you have to define that, this is how you're going to define that. Okay, the power to which the molar concentration of a reacting species is raised to in the rate law. We say we have basically three types of order of reaction. Let's consider reactant A and product B. The rate of chemical reaction is proportional to conc of A, right? If I'm to remove this sign, I'm going to have the rate is equal to what? K conc of A, right? To the power of what? X. Where S here represents what? Order of reaction. Now if I have B, A plus B, that will give us B, right? To the power of what? Y. Okay. But let's consider just this, because I'm going to use it now to explain what order of reaction is all about. Now listen, S represent, either X or Y represent the order of reaction. We have three basically types of order of reaction. We have S equals to 1, or S equals to Y equals to 1, S equals to Y equals to what? 2, S equals to Y equals to what? 0. Meaning, whenever your X or Y is 1, it means first order. First order means when the power or the exponents to which the molar concentration of a reacting species, if it is 1, it is called what? First order reaction. Meaning that if I have here to be Ka to the power of 1, this means first order reaction with respect to what? To A. With respect to reactant A, it's first order reaction. But when this power here, this X here, is 2, this means that it is second order with respect to what? To A. But let me just bring them out. If I have R equals to K, A to the power of 2, then R equals to what? K, A to the power of what? 0. A raised to the power of 0 we know is what? Is 1. Anything raised to the power of 0 is 1. So 1 times k, this is also what? K, right? 1 times k is k. So for the first one, we have power 1, meaning this is called first order reaction. For this, we have power 2. This means what? Second order what? Reaction. For this, what does that mean? It means 0 order reaction. And that will give us what? K. All of this, we call them what? We call them differential rates expression. They're all differential. Differential rate law. Rate law for first, second, and what? 0 order what? Reaction. But what is first order reaction? What is second order reaction? What is 0 order reaction? Now, when you hear the word first order reaction, what comes to your mind is that the power of the exponent to reach the molar concentration of any reacting species is raised to the power of 1 is called first order reaction. I repeat again, first order reaction, this is when the molar concentration of a reacting species is raised to the power of 1. It's called first order reaction. All right? Okay. And let's take them one after the other. Let me not rush us. Please, guys, take notes because I'm almost rounding up with this part. Then we can go into calculations and all that. So we're looking at first order reaction. Please, guys, if you are following, indicate that you are following. If you are following, indicate that you are following. I want to know that you are following. If you are active, indicate that you are active. If you are active, please indicate that you are active. Indicate. Okay. So for first order reaction, we say that if we have reactants to form product B, then rate of chemical reaction is equals to K to the conc K times concentration of A. The power here is 1, right? Okay, and we have defined that. We say that to define first order reaction, what do you tell them? In first order reaction, this is when the molar concentration of the reacting species, right, is raised to the power of what? 1 in the rate law expression, right? It's power of 1. And one thing again you should take note in first order is that in first order reaction, if the concentration of the reactant, what is our reactant here? Reactant A is doubled. The rates will also double. The rate will also double. If the conc of this reactant is doubled, the rate will also be increased by a factor of 2. If the concentration of the reactant is double means increased by a factor of 2. That means the rate will also increase by a factor of 2. What does that mean? Is that rate equals to what? If we are saying that the whole of this is what? Is times 2. Then my rate becomes what? 2K. What notice here? Don't forget this is our constant. Okay, that means that the rate of reaction is doubled here. By what factor? By a factor of 2. That's for first order reaction. So after defining it, then tell them that if the concentration of the reactant, that in first order reaction, if the concentration of the reactant is doubled, the rate of reaction will also double, which is what we just saw. Then the other one, second one, is called second order reaction. Please note this. For second order reaction, if we have reactant A forming B, second means that the power here is 2, don't forget. Meaning the value of our X is equals to 2. Now what does that mean? That if the concentration of the reactant is doubled, the rate of reaction will increase by a factor of what? We increase by a factor of 4. We increase by a factor of 4. But let's define second order first. Second order reaction, okay, is defined as this is the power to which the molar concentration of the reacting species is raised to the power of what? Of 2, right? To the power of 2. But this is when the molar concentration, the power or the molar concentration of the reacting species is raised to the power of what? Of 2. This is when the power of the molar concentration of the reacting species is raised to the power of 2 in the rate law expression. The same way we define first order reaction. The same way, just remove 1 and put what? 2. All right. Now, but hello guys, are you guys still with us? Network is very bad there. Please, please, if you are active, please indicate that you are still active. Network is very bad. Please, if you are active, indicate that you are active. If you're active, indicate. Very bad, yeah. Can we proceed? Can we proceed? Okay, let me quickly, sorry for that interruption. This is the challenges with online class and all that. So please, we are looking at the last one as zero order reaction, where we say the value of x is equal to 0, right? And we have seen that in zero order reaction, this is when the power of the molar concentration of the reacting species is raised to the power of 0. Meaning when the value of x and the power here is 0, so anything raised per 0 we know in the law of indices is what? 1. So a to the power of 0 is 1. So 1 times k is k. So that means for this, if the count of the reactants is doubled or increased, the rate of reaction will remain the same, will not change, right? Will not change, or we remain the same, right? Meaning that our rate is equal to, if we double this 2, let's look at this. Okay, we have 2 to the power of 0, meaning our rate becomes what? K times 1. So our rate is equal to what? K, meaning the rate remains constant. K represents constant. So in zero order reaction, our rate is always constant. It does not change either. Okay. Now let's look at differential rate equation and half-life. What is half-life in chemical kinetics? What is half-life in chemical kinetics? Half-life is defined as the time taken for half the initial concentration of a reacting species to be consumed. Half-life is the time taken for half the initial or original concentration of a reacting species to be consumed. Please take note. By definition, half-life is defined as the time taken for half the initial or original concentration of a reacting species to be consumed. You have to take note that we have half-life for first order reaction, for second order reaction, and for zero order order reaction. We have half-life for first order, second order, and zero order reaction. Now, I'm going to show us the integrated rate law for each of these half-life. I say we have rate law. Rate law is of two types, right? We have the differential, right? Differential rate law. I want to explain what that means. Number two, we have what we call the integrated what? Integrated rate law. Under differential, I've been able to show us how to express first order. First order is Ka, right? Second order is R equals to what? K, A raised power 2. Zero order is R equals to what? K, right? All of these are called what? Differential. Differential rate law expression shows us the expression between concentration and what? And rates. How changes in what? In the concentration affects what? Rate of chemical what? Reaction. But let's look at integrated rate law. Then from integrated rate law, I will now bring out formulas for calculating half-life for each of these order of reaction. For each of these order of reaction. Please, if you are still following us, indicate. My network is very bad here. If you are still with me, indicate you are still with me. Please, if you are still active, indicate that you are active. If you are active, please indicate that you are active. If you are active, indicate that you are active so that we can proceed. Well, let's look at what we call integrated rate law expression. Rate law. The first one we look at is for first order reaction. First order reaction. I won't be integrating. All of these have their integration, how to integrate to get the formulas. But because of this exam focus, I'll just be listing out the formulas. So I will not bore us with a lot of things. Okay. The formula says that final concentration is equals to initial concentration, all right, minus what? Rate constant times time. That's the first one. Then under this half-life for half reaction first, then half-life for zero order reaction is T half, which is equals to about initial concentration divided by what? By 2K. By 2K. Please take note of this. Or we can say half times initial conc over what? Over K. Then the next, number 2, is first order reaction. First order reaction. For first order reaction, we're going to have ln A equals ln A naught. That means initial concentration minus what? Minus KT. Please, if you are following, please indicate that you are following. Hello guys, the network is very bad. If you are active, indicate you are active. Okay, these are the integrated rate law formulas. Okay, these are the integrated rate law formulas. For the first one, we have the zero order reaction. Here we have final concentration of the reactant. 80. 80 means half-life for first order reaction is 0.693 divided by K, where K represents our rate constant. Then the third one, which is second order reaction, the formula says, the integrated rate law formula says 1 over what? 80 equals 1 over A naught plus what? Plus K. Then half-life for second order reaction is C half equals 1 over K A naught. Let me give you guys a little bit time to write out this. Please write it out, because I'll be solving some problems with this now. Just write out this for me. Okay. Write this out if you are done. All right, so now the next question I want us to look at. Expect this question in your exam. Expect this question in your exam. Very important question. I want you all to expect this in your exam. The question says that explain the factor that affects rate of chemical reaction. Explain 4 factors rather that affect rate of chemical reaction. I believe that we can all solve this, right? Good. Then the next question, question 2B, says position of hydrogen iodide into hydrogen and iodine is a second order reaction. I repeat again, the decomposition of hydrogen iodide into hydrogen and iodine is a second order reaction. The constant K, the rate constant K is given as 0.08, okay, liter per what? Per mole. Question says, how long does this take an initial concentration of 0.05 mole per dmq or mole per dmq to decrease to half this concentration? How long does it take 0.05? So that means our initial concentration was given as 0.050 mole per dmq. Okay, mole per dmq. All right, let's look at this question. How long? How long simply means what is the half-life? Is that clear? What is the half-life? I repeat again, the decomposition of hydrogen iodide into hydrogen and iodine. We are told that hydrogen iodide decomposed into hydrogen and iodine, right? And this decomposition follows what? Follows second order reaction. It follows the second order reaction. And we are told that our rate constant K is given as this. Then the initial concentration of the reactant was given as 0.050 mole per dm cube. Then the question says that how long does it take an initial concentration of this to decrease to half this concentration? When you hear the word to decrease to half, that means half-life. What do we say is the half-life for second order reaction? Half-life for second order reaction. Let's find out what is our half-life for second order reaction. Don't forget that recall that for second order reaction, I gave us the half-life is given as 1 divided by K times initial concentration of A, right? If we are considering A as the reactant, so half-life for second order reaction is given as 1 divided by K times this. This is a simple equation, okay? We already know that our K is given as 0.08 and the initial value of A was given as this. That means our half-life becomes what? 1 divided by, our value of K is 0.08 times initial conc of A is 0.05. All right. So by the time we multiply this, that will give us, multiply this together and divide 1 by this. The total answer we're going to have will be 250 seconds. 251 seconds. Please take note. When you multiply this, then divide 1 by the value here, the answer will be 250 seconds. So this is how simple this question can be. The next question, question 2C. 2C says that given that the half-life for first order decomposition of iodine chloride, given that the half-life for first order decomposition of iodine chloride, please, if you are following, indicate that you are following. Okay. Given that the half-life for first order decomposition of iodine chloride is is 1 point. Given that the half-life for first order decomposition of iodine chloride is given as T half equals 1.08 times 10 to the power of 4 seconds. Then we have to calculate the rate constant to find the rate what? Constant. We are told that given that the half-life for first order reaction is given as this, then find the rate constant. This is also very simple solution. Don't forget that recall that half-life for first order reaction is about 0.693 divided by K. So that means our K here is going to be 0.693 divided by divided by T. By the time we cross multiply this and make our K as subject, then my K becomes 0.693 divided by T half. So by the time we divide, the value of K here will be 0.693. The value of our T half-life was given as 1.08 times 10 to the power of 4. So let's divide and see what we are going to come out with. Let's divide and see what will be the result. When you divide this with this, the value of K will be about 0. Divide 0.693 by 1.08. That will give us about 0.65 per second. Okay. Here we have, when you divide 0.693 by 1.08, we're going to have this. When you move this 10 to the power of 4 upward becomes what? Minus 4. When you divide this with this, that will give us 0.642. Then times 3 per minus 4. When you move your points a little bit with 1 unit, that will give us 6.42, because the rate constant here is defined from first order reaction, right? From first order reaction. Look at it here. The unit of the dimension of 0.693 is 1, is a constant. the dimension of time. This TR represents time. That is second, right? Okay, that will give us per second. So our K is simply per second. All right. So please take note of that. Let's look at another question. Another question. Okay, hello guys. So can we proceed? Network is very bad. The network is very, very bad. Very, very bad. Very, very bad. Please, if you are following, indicate that you are following in the comment section. If you are following, indicate that you are following. If you are following my network, yeah, I have to just switch network. If you are following, for this question, we just finished solving. We are told that the rate of a reaction follows first order reaction, and we are giving the half-life to be 1.08 times 10 to the power of 4 seconds. And we also find the rate constant. The rate constant. But don't forget that half-life for first order is T half equals 0.693 divided by K, right? So if that is true, that means that to find our rate constant is just the inverse. That means I will make my K to stand alone as the subject of the formula. Here becomes 0.693 divided by T half. All right? The dimension for this constant is 1. While dimension for time is seconds. That means the unit of this K is per second. Per second. But let's see how we solve this. So we have K equals 0.693 divided by 1.08 times 10 to the power of 4. When you divide 0.693 by 1.08, that will give us 0.642. Then when we move this 10 to the power of 4 up, it becomes what? 10 to the power of minus 4. Then in the proper standard form, I'll move my point forward, right? Here becomes 6.4 times 10 to the power of minus 5 per second. So the unit of K for first order is simply per second. Please take note of that. It's per second. All right, so let's solve for that. Let's solve for that. Sorry, the network is very bad. I hope you guys are following. If you are following, please indicate that you are following. If you are following, indicate that you are following. Yes, someone said it's hanging. I know it's hanging. My network here is very bad and it's really disturbing me. I'm not happy with this. And this is the only time we have to learn because by 8 p.m. tonight, I'll be very busy with Night of Revelation because we are meeting by 8 p.m. at my center. We are meeting and this is just the only time we have to learn. All right. So let's see how far we can go. Let's see how far we can go. Okay. All right, guys. So let's move on. Let's move on. The next question I want us to look at. All right. I want to believe that we are all following. Let's check out for other questions under this. If you are with me, still you are with me. My network is so bad. Okay. Be patient a little. Alright, this same question will just appears again. So I think we have exhausted it. The composition of hydrogen iodide and into hydrogen and iodine is a second order reaction. So no need of going into that again. That's good. So in case it appears again, you can be able to tackle this question. I want to make sure that we have exhausted everything under rates of chemical reaction. By now, we should all know how to define the terms, right? All of those terms there. Okay. So let's see what next again we have here. Under rate of chemical reaction. Just be patient with me. Be patient with me a little. Be patient a little with me. Be patient. If I should go through and I didn't see any, then we can move into something else. Just want to be sure that we exhausted everything under rate of chemical reaction. If we do not see any, we move into something else. Okay, I don't really know. Let's look at this question. It's a kind of lengthy, but let's just exhaust this part. Okay, we are given a table. In this table, we have our serial number. We have here to be. We have concentration of NO. Okay, molarity, that is mole per dmq. Then we have that of hydrogen gas, also in mole per dmq. Then we have our rates. Our rate is molarity per second. Molarity means mole per dmq, then per what seconds, okay? The word molarity means mole per dmq, right? So that means the full expression for this is simply this, right? All right, so let's look at in the first experiment, second experiment, and third experiment. In the first here, we have 0.0250. Here we have 0.010. Here we have 2.4 times 10 to the power minus 6. Second experiment, we have 0.0250. Here we have 0.005. Here we have 1.2 times 10 to the power minus 6. Third experiment, we have 0.0125. Here we have 0.010. Here we have 0.6 times 10 to the power minus 6. And we are not giving the kinetics. Or giving the equation. The equation given to us is 2NO plus 2H2 to produce 2 water plus nitrogen gas. Then we also find, number 1, order of reaction with respect to nitrogen 1 oxide and hydrogen gas. Number 2, find the overall order of reaction. Number 3, find the overall order of reaction. Number 3 is give the empirical rate law. Give the empirical rate law. Number 4 says find the rate constant. which is our K. This was given to us, and I have to just pick this from your textbook in case IMSI will just say this as part of your exam. All right, this is from your textbook, those in Imo State University. We are given the table here. We have experiments, the molar, here we have the conc of NO, we have conc of what? H2. The word conc means concentration. Okay, so conc of NO for this first experiment is 0.0250. That of H2 is 0.01. Then the rate of reaction is 2.4 times 10 to the power of minus 6. Then for experiment 2, the conc of NO is 0.0250. Conc of H2 is 0.005. Then the rate is 1.2 to the power of minus 6. Then also the third experiment and all that. Then we are asked to find the order of reaction. Don't forget that we say that if we have reactant A plus B to give us C plus D, we're able to define the rate law expression as rate is equals to what? K, conc of A to the power of X, and conc of B to the power of what? Y, right? This is called the rate law expression. The rate law expression for this reaction is R equals K times conc of A to the power of X times conc of B to the power of Y, where X and Y represent the order of reaction, right? Good. Now, for this, we have two reactants here. We have NO and H2. That means that by rate law expression, the rate law expression is going to be, we are solving, let's solve, solution is going to be rate equals to K. K, the first one we have here is NO to the power of X, and H2 to the power of what? Y. Don't forget, H2 to the power of what? Y. The general expression is this. So we are using this to form this. Our A, this is our A, that represents our NO. This is our B, that represents what? Our H2 to the power of Y. Now, what do we need to do? What we need to do now is to find the rate of reaction with respect to what? With respect to NO. Question said find the order of reaction with respect to NO. Number 2, with respect to what? H2. All right? Okay. By now, we know what is order of reaction, meaning find the power to which the conc of NO is raised to, or find the power to which the conc of H2 is raised to. To find the order of reaction with respect to NO, we have to keep H2 constant. Please take note. To find the order of reaction with respect to NO, to find this, I have to keep this constant. What does that mean? Is that I'm going to ask myself, where is H2 constant here? Where is it constant? It is constant in experiment 1 and experiment 2. To find the rate of reaction with respect to NO, this is like saying X, right? This is like saying what? Y. Don't forget, NO represents X, H2 represents what? Y. So that means that to find the value of X, I'm going to look for where Y is constant or where H2 is constant. Then also to find the order of reaction with respect to H2. H2 means to find Y, right? It means I'm going to look for where NO is constant, which is 1 and what? 2. Constant means at what point in this table is the value of NO the same, right? And at what point is it in this table is the value of what? H2 the same. Now, the order of reaction with respect to NO means I will go to H2 table and ask myself, where is H2 constant? It's constant in experiment 1 and experiment 3. That means I will use this to represent my R1. This will represent my what? My R2. I'll repeat again. To find the order of reaction with respect to NO, let's solve for NO first. For NO, I will keep H2 constant, meaning I'm going to look for where H2 is constant, which is 1 and 3, right? Why is it constant? 0.010 is same as 0.010. So this becomes, experiment 1 becomes our R1. This becomes what? Our what? R2. So to find R1, the general rate law expression for this reaction is R equals to K NO to the power of X and times what? H2 to the power of Y. So for R1, just look at what I mean. For R1, that will give us K in brackets. My NO here is 0.025, 0.025 to the power of X times my H2, because here we have H2 here, that will give us about, our H2 is 0.010 to the power of Y, all equals to our rate constant here, our rate rather, is 2.4 times 10 to the power of minus 6. Then for R2 is simply this. R2 becomes what? K in brackets. Here will give us what? 0.0125 to the power of what? X. Then the next is 0.010 to the power of I, all equals to what? 0.6 times 10 to the power of minus 6. Don't forget that we are looking for order of reaction with respect to what? NO. I will say that to find NO, I have to look for where H2 is constant. And we have seen that it is constant in experiment 1 and experiment 2. So every value of experiment 1 is taken as R1, which we just did, using our rate law expression. So for my R1, my NO is what? 0.0250. My H2 is what? 0.01. Okay, are we seeing what happened here? All right. 0.0250 is same as this, okay? 250 to the power of X. Please don't forget. All right, so the next is to divide. I will divide R1. I will as well divide R2 by R1. But let's divide smaller. 2.4 is bigger than what? 0.6 is, right? So that will give us this. If I could divide this with this, what you notice here is that the value of K, we cancel K, right? When divide R1, the entire value of R1 what R2, meaning that K will cancel out K. Likewise, this will cancel out this. Don't forget, this will also cancel out this. Now we are left with this and this, right? Meaning 0.0250 to the power of X divided by what? 0.0125 to the power of what? X. All equals to, when you divide 2.4, let's go. 10 to the power of minus 6, we cancel what? 10 to the power of minus 6, right? We are left with what? 2.4 divided by what? 0.6. Okay. Let's see what we are going to have after then. Are we ready? All right. So by the time we divide this will give us 0.0250 divided by 0.0125 all to the power of S, right? All equals to what? Divide 2.4 by 0.6, that should give us about 4, right? Then divide this with this, we're going to have 2 to the power of X equals to what? Here, 4. So from here, I'm going to express the base to be the same. Here, I'm going to have 2 raised by S equals to 2 raised by what? 2. If the base are the same, they can cancel out, right? I can then equate the power. That means my X is equals to what? 2. So what you notice here, that the value of X is what? Somebody is 2. That means with respect to NO, it is second order reaction. With respect to NO, it is what? Second order reaction. With respect to NO, it is second order what? Reaction. All right. Okay, take note of that. the second order reaction. Now, with respect, you can write this out with what? With respect to what? To NO, it is second order reaction. Please take note of that. Now, the next is to find with respect to what? With respect to H2. To find with respect to H2, what do we say will happen to NO? I will make NO constant, meaning I'll look for where NO is constant. Where is it constant? In 1 and 2. So I will call this RO1 again, then call this what? RO2. Or we can call it RO3 and RO4. Alright? But let's just repeat the same thing. Let's call this RO1. This is what? RO2. Alright? So with respect to what? NO. With respect to H2 rather, we'll keep NO constant. It's constant here and here. I mean, the value of NO is the same in 1 and 2. So that means this becomes my RO1. It becomes what? My RO2. Now let's move on. Please, if you are following, indicate that you are following. Indicate that you are following. If you are following, indicate that you are following. Indicate in the comment section. I hope you guys are following. I hope you are following. I hope you are following. I hope you are following. I hope my RO1 becomes what? My RO2. Now let's move on. If you are following, indicate that you are following. What? RO2. Or we can call it RO3 and RO4.